So let's continue. So what you see here are very important things that you don't have to remember all the details, but it's important that you have a big picture. That's resonance curves, or let's call them that's response functions. When you have an excitation which is characterized here by the ratio of the the frequency of the excitation to the natural frequency, and on the vertical axis you have the response amplitudes normalized. Linear response. As you see here that when the dissipation goes down and down and down, the peaks go up and up and up, and if the dissipation is zero, theoretically the amplitudes are infinitely high. In reality, of course, you cannot have infinitely high stresses when you deal with singularity. You cannot have infinitely high amplitudes. But this model is still very useful. Let me actually tell you what happens and what doesn't happen in a situation when the amplitudes are getting very high. You remember I mentioned to you about an hour ago that when you have high amplitudes, you have nonlinear response, and here everything is linear. There was a famous Russian physicist, Mandelstam, used to say that any idealization takes a revenge for itself. In other words, if you idealize something, the idealization works in certain limits, it doesn't work outside these limits. What actually happens when the amplitudes go up and up and up? The vibrations become nonlinear, and we will show that. I will show that later on, when the situation when you have a membrane forces, that's a nonlinear equation with so-called rigid characteristic of nonlinearity. In this case, this resonance curve will, first let me show you the linear curve. The linear curve looks like this. The nonlinear curve, let's say that this is the situation when the frequency of excitation is equal to the natural frequency, and therefore the response amplitudes are infinitely high. In reality, with a nonlinear system, with a rigid characteristic of nonlinearity, the situation will look like this. And this is linear. This is nonlinear. What will actually happen, an interesting thing, if you are here, and first of all, as you see here, the amplitudes are never infinitely high. Why it happens? Because in this nonlinear system, approximately, let me put it this way, the frequency of a nonlinear system can be calculated as the frequency of the linear system plus a certain parameter of nonlinearity times the amplitude squared. And it's true, when the amplitudes are low and the amplitude squared is even smaller quantity, in this case the nonlinear frequency is the same as linear frequency. But if the amplitudes are high, they're starting getting higher and higher and higher, the frequency of vibrations, the actual frequency of vibration starts getting different and different from the linear frequency, and that means that's why people say nonlinear systems destroy resonance conditions. Therefore, the resonance conditions, classical resonance conditions, can exist only in linear systems. In nonlinear systems, if you will start increasing the frequency of excitation, you'll go this way, this way, this way, up until this, and then all of a sudden it will jump here and you will continue to go this way. On the other hand, if you will start going in this direction, you'll go this way and this way and this way and this way and this way, this way, up until this point. Then it will jump up and go this way. All these interesting phenomena exist in nonlinear systems and do not exist in linear systems. The only thing that we want to know, that's why I'm emphasizing that, because in electronic equipment we quite often, even with very maybe unrealistically even low drop heights, like I mentioned to you, just maybe less than an inch, a very thin, a very flexible printed circuit board exhibits very significant membrane in-plane forces, and the situation, if you substitute the drop height with the frequency, vibration frequency, you'll end up with a situation something like that, rather than a situation that something like in a linear system. The other important thing that I want to emphasize, look now at the view graph of the resonance curves, is that if the dissipation is high enough, as you see for the curves which are located at the lower portion of the plot, you don't have any vibrations at all. And it's a useful curve that should be developed, used for a particular structure. This curve, as a rule, should be obtained experimentally. You can calculate with high accuracy the frequency of vibrations, undamped vibrations. You can certainly evaluate with high accuracy the inertia forces if you know the mass and acceleration. It's very hard to predict. There are many good theories, and none of them works for all the cases in their lives for how to predict and to evaluate the dissipation. Therefore, in each particular case, you want to generate these curves experimentally. Now I will describe a particular problem that we have encountered many years ago in Bell Labs, and that's effect of viscous damping on the dynamic response to impact loading. Here's the situation, and it's published. I will not go into all the details, but I want to show you what is the result of this analysis, although here it's described in words. Let's say that here you have a certain parameter which is responsible for, let me call it this way. I believe it was a ratio of this parameter to the frequency with the 2 here. And here is, let's say we have accelerations and we have displacements. Let's say it's maximum acceleration and maximum displacement. And this will be, we have a system which is described by these equations, which is in the upper equation, but instead of having here a harmonic force with a harmonic frequency lambda, let's say that we have simply 0 on the right-hand side, but the initial conditions are such that the initial displacement is 0, and the initial velocity can be calculated as an impulse divided by mass, and that will generate vibrations due to an instantaneous impulse. But in this case, it will be also, I examined the situation when we drop a viscous system, let's say the system that you see on this picture. You drop everything not in a rigid floor, but on a highly viscous medium, like highly viscous grease or something like that. Intuitively, you can feel that if it's a highly viscous, that means the acceleration might be huge, if it's indeed highly viscous dissipation. On the other hand, if there is no dissipation at all, the acceleration can also be significant. Intuitively, it's felt that should be a certain level of viscosity that brings down the induced acceleration as a result of drop tests. And indeed, for the acceleration, this curve will look like this. And this is for the maximum accelerations. When you drop a system with a viscosity either on a viscous fluid, viscous grease, or if it has some viscosity inside. However, as far as the maximum displacements are concerned, they will always go down and down and down with increase in viscosity. Important thing, and we will discuss that a little later, that what actually want when you use protection of portable electronic devices against drop impact. You, generally speaking, you want to kill two birds with one stone. You cannot afford to have a significant dropping distance, or let me call a significant braking distance, let me use this term. And at the same time, you want to have a small braking distance, so the braking distance is from the moment when the vulnerable device touches the floor to the moment, and that in this case the velocity is the maximum, and then the end of this displacement is when the velocity is zero. So you want to have this distance, braking distance, as short as possible. At the same time, you want to have the deceleration also as low as possible. It's clear that you can't have both, and therefore probably the best thing to have or to use the product as K maximum displacement times maximum acceleration, deceleration. In this case, I'll use this with a minus, to have this quantity as small as possible. So therefore, you can somehow to use a criterion, and we will come back to that later on, so that I'll add more physics to that. But as far as this part is concerned, it's important that when we consider some level of viscosity in order to bring the response down, we should ask ourselves, what are we interested in? If our system is able to withstand very high acceleration, decelerations, it's fine, it's excellent. In this case, we will take care only of displacements. But if the system cannot withstand high accelerations, in this case, we have somehow to come up with the best compromise between the low braking distance and low enough decelerations. And this paper, this analysis, shows you within the framework of a linear analysis, which looks like it works in this case, that how to design such a system so that to obtain the minimum deceleration, acceleration possible. And so here the summary says viscous damping always reduces the vibration amplitudes, but if damping is significant, could lead to elevated accelerations, which might exceed considerably the accelerations, decelerations of the non-damped vibrations. If viscous damping could be controlled, it should be made low enough to lead to sufficiently low accelerations. And the paper with all the details, explanations, and extension is published in IEEE CPMT transactions. Again, CPMT stands for Components, Packaging, and Manufacturing Technology. Another example has to do with heavy electronic components, and also I'll discuss here as illustration to the general, to the basics that we have discussed earlier, in using an example of heavy electronic components. What you see here is you have a printed circuit board, and on this printed circuit board, it's mounted a heavy electronic component. Let me repeat it here for the sake of clarity. Let's say you have a printed circuit board. And for heavy electronic components, even today, people don't use surface-mounted devices because the interface between the surface-mounted device and the printed circuit board is too weak to be able to withstand vibrations if you have a heavy component. Let's say you have a heavy component, power component, and you have supports, and certainly it goes through hole, and it's soldered here, and it's soldered here. So you have a situation when this printed circuit board is subjected to vibrations, let's say in this direction. So it starts vibrating this way. Of course, these vibrations get transmitted to the heavy component, and the component starts vibrating this way. And certainly, this is where the most vulnerable spot is. And certainly, you want to analyze that, and you want to understand how vibrations of this printed circuit board induced by external excitation, how they are transmitted to this component, and how that results in elevated stresses here. And of course, it could be, you can consider what I consider two cases when you drop this, and therefore after that it becomes subjected to like free vibrations, or if you apply here sinusoidal excitations, and because of that, this component starts vibrating. And that's what you see on this view graph. And I'll simply read you the results. First of all, of course, it was a challenge and an interesting exercise, mechanical, to evaluate the frequency of a system like this when you have, of course, you can find in every book on vibrations, if you have this entire mass, if it's boiled down to a lump mass, and it's put on a component on a board, and in this case, you can simply consider that as this beam as the electrical lead as a cantilever beam with a lump mass at the end. That will be much simpler than the real life when it's not a lumped concentrated mass, but the electronic component has a configuration approximately what you see on this picture. And this is published in ASME, American Society of Mechanical Engineers, Journal of Electronic Packaging. And the results that the obtained formulas for the natural, first of all, you want to evaluate the natural vibration frequencies of this structure, because the position of the center of gravity for this device is very important from the standpoint of its natural vibrations and also its length of the device. Dimension in the vertical direction is important. So the obtained formula for the natural vibration frequency of the electronic component considers the radius of inertia of its mass. So in other words, it's mass and length, the distance of the center of gravity from the outer free end of the electric leads, and the flexural rigidity of the leads and their number and the length of the leads themselves. And the numerical example was carried out for the actual case when the radius of the two leads was 0.5 millimeters. The Young modulus of this material was copper was 16,000 kilograms per millimeter squared. The length of the leads was 5 millimeters. It was actual AT&T design at that time. And the component's weight was 50 grams. And the calculated frequency was 3.8 0.29 Hertz. But if the component's mass were considered as a lamp mass concentrated at the lead's ends, which you can find in the literature, then the computer natural frequency would be much, much higher, as high as 13,689 Hertz. So the fact that to consider the actual length, the actual situation, was not just a small difference, but a significant difference by a factor of 4. And of course, that's why, again, as we have discussed, you have to know, first of all, to have natural frequencies of free vibrations to make sure that you will be able to avoid resonant conditions. And the other problem is when you have actually the curve, what you see here, the curve of actually of this type, exactly of this type. But what's not doesn't look exactly like that, because this is the real life of this particular system, this particular component. But it looks approximately like that, and a linear approach was used. That's why the maximum amplitudes at resonant conditions, where it's 1, are infinitely high, and actually that means that the external frequencies with which the printed circuit board is vibrated are equal to the natural frequencies of the system, which is printed circuit board, primarily due to the heavy component. And as you see from this resonance curve, the response functions has a strongly pronounced peak at the resonant frequency, rapidly decreases to 0 with a decrease in the excitation frequency, and decreases slowly with an increase in the excitation frequency. And the most effective means, as you see from that, a practical result, the more effective means to ensure high dynamic stability of the system is to make the frequency ratio below the resonance value. Because then if it's below the resonance value, you have a dramatic decrease in the amplitude. That's above the resonance value. You have a decrease at the beginning. It will be significant, then it will not be that significant. But it's very important that there exists a certain high frequency of excitation, close to 11 here, above which the response function is 0. In the executive example, this frequency is by a factor of almost 11 higher than the natural frequency. So if you do this kind of analysis, by the way, the system was built based on this analysis, the actual AT&T system, and the results, the test results agreed excellently with the predicted data. By the way, the prediction is always better in a situation for a linear system than for a nonlinear system, for obvious reason, because the mathematical equipment already is well developed and is well known. Although later on I'll show you that I was fortunate to obtain also an exact solution to a highly nonlinear system, but that we'll probably be discussing that most likely either in the late afternoon today or maybe tomorrow. Random vibrations. As I said, in this course I will not go into the details of random vibrations, too complicated. Those who are interested can take my book that was published in 1997 by McGraw-Hill, Applied Probability for Engineers and Scientists, and there is a lot of information there about random vibrations, random phenomena, and many, many things, and simple and not that simple, and everything. A book is a book. And therefore, the many problems were approached there from different points of view. So it's almost everything about random vibrations that, no, I shouldn't say everything. There's never everything, but there's a lot about random vibrations. But here I'll quote first Francis Bacon, the famous English philosopher and statesman, who said, "If a man will begin with certainties, he will end with doubts." But if he will be content to begin with doubts, he shall end with certainties. Well said, almost correctly said, and therefore many deterministic solutions are just academic, and in the real life we have to consider deviations from certainty, and you can do that in many ways. But here I'll only describe why we need that. So why random vibrations? First of all, quite often, as I said, the life is not as simple, as predictable as we would like to have it, and therefore we want to consider and what happens if the prediction will not be, or the input data will not be exactly what we think they will be. Those people without any random anything, we all know that if, with the best algorithm, the best model in the world, if the input data are shaky, you have a situation which is well known by the saying garbage in, garbage out. We all know that. But at the same time, the real life is even, I would say, more malicious. So what it means that even we might have the best, the most precise, the most accurate input, the system is such, the materials are such, the behavior is such, that it itself generates some uncertainties. Of course, the ability to understand these uncertainties, to predict them, to minimize them, and certainly, and it's very important. We all know, going back to physics, a famous principle of uncertainty of Heisenberg's uncertainty, that the position and the momentum of a particle cannot be known exactly. It's only their product might be, and so that's called the principle of uncertainty. It's a very important fundamental principle of quantum mechanics, but it's much less fundamental in our aero engineering, but it's also true in many cases when uncertainty is generated by the nature, it's not a level of our ignorance. The nature itself is uncertain, and therefore when we understand that and model it properly, it will make our design much more reliable and predictable and consistent. Modeling of nonlinear random vibrations is certainly a challenge, and it's still, you all heard about the chaos in dynamic systems, a phenomenon, of course, it's well beyond this course, although in my book I describe it, but it's, when you model nonlinear systems, even the excitation might be linear, might be deterministic, but the nonlinearity itself very often generates like quasi-random response, and it's true not only about multi-degree of freedom systems, it's also true about single degree, provided it's highly nonlinear. So that phenomenon is called stochastic instability. Too complicated for this course. I'll not go into the details, but those who are interested, please get back to me, and I will be happy to even launch a project with you on that, and to understand when we want to bring in random to stochasticity or probability, to understand what happens when the nature is unpredictable or when the system itself contributes to uncertainties. But doesn't mean that we should say, I quit, I don't know what to do. Not the case at all. We can predict how the system will behave in the conditions of uncertainty, because we describe these uncertainties with certain probability functions. So on the probabilistic level, the prediction is certain in terms that we know the probability of failure. For instance, one of my projects now with one company is this. I call it probabilistic design for reliability. What it means that I run accelerated life testing based on I run these tests for the most vulnerable elements in the system, let's say for solder joints. Then based on that, for this vulnerable structural element, I predict the probability of failure under the given conditions of loading after the given time and service. It's clear that at the beginning the probability of failure might be lower than later on, about 2 years, 5 years, 10 years in operation. Then based on this data for the most vulnerable element, based partially on accelerated life testing, partially on probabilistic modeling, I can predict the probability of failure for the entire subsystem, the entire module, and then put together a actual device module and test it. I did that 3 or 4 times in my professional life in application to different systems, not necessarily electronic, and I was pleasantly surprised that the predicted probability and they actually measured, and after extensive tests, the measured probability, predicted statistical probability of failure were in very good agreement. Now, finally, as far as random vibrations are concerned, I want to say that today we have shakers that are designed to generate random vibrations, even for systems that will probably not see any vibrations, including random vibrations, in their actual operations. Because it has been established, I mentioned that a couple of hours ago, that applying vibrations and using shakers is a good means, a good tool to weed out infinite mentalities. The challenge here is to determine the right width and the right ordinates of the excitation spectrum. And the spectrum is you have different amplitudes for different frequencies. And it's important that this spectrum is wide enough to cover all the actual natural vibrations of the system, the first, the second, maybe the third. But low enough not to introduce permanent damage. For instance, certainly you don't want to introduce damage that will consume a significant lifetime of the device. Now, since I mentioned several frequencies, I want to indicate the following. As a rule, we are interested, first of all, in the first lower frequency, unless we have a sinusoidal excitation with a certain frequency, and this frequency of the excitation is not close to the lowest frequency. It might be close to one of the higher frequencies, and this, yes, we want to predict the resonant condition for high frequencies. In this case, we want to know the high frequencies. But for instance, when for drop tests, and for many other situations, we are interested in the lower frequencies because, as a rule, typically it's the lowest frequency that frequencies that are associated with highest amplitudes. And the reason why they're associated with higher amplitudes, because the dissipations that exist, damping that exists in any system, first of all, suppresses the high frequencies. And therefore, although theoretically, hypothetically, you can have all the frequencies in the world, particularly if the excitation is close to instantaneous impulse, it's also well known or established, proven, that the shorter the excitation is, the wider is the frequency spectrum that it generates. By the way, that's also one of the corollaries of the principle of uncertainty in application to dynamics. So that's why it's, in reality, in practice, it's important to be able to predict the first, the second, maybe the third frequencies, and we can forget usually about high frequencies. The other important thing that I want to indicate as far as random vibrations are concerned, if you have a wide spectrum I mean wide in terms of the range on which the amplitudes are changing. And you apply this random spectrum to a system, like to the system that we just described, which you have a heavy electronic component mounted on the printed circuit board. The dynamic system behaves as sort of a like narrow band filter that enhances the frequencies which are close, the excitations with the frequencies which are close to the natural frequencies, and suppresses excitations which are not close to the natural frequencies. Well, it's an interesting and important phenomenon and important quality of a dynamic system. That means quite often we don't know in advance what the natural frequencies are, and it might not be that easy to predict them. And the procedure, why you can apply excitation. Harmonic excitations actually use this resonance curve to determine natural frequencies. Look, what you can do, you don't know what the natural frequency is, and it might not be that easy to calculate that, to predict it by modeling. What you can do, you can increase, start increasing the frequency of excitations and measure the amplitudes. When the amplitudes reach the peaks, that means you are close to resonance conditions, and that means this is the first natural frequency. Then you keep going, then you have another peak. That's the second natural frequency, and so on. So that's an effective experimental way, by the way, to evaluate the natural frequencies. But if you don't want or cannot do this procedure for one reason or another, this procedure, you're not happy with the results, you can simply go ahead and apply a random excitation, and you will see several peaks on the right away on the response, and these peaks will correspond to the natural frequencies, because, as I said, the dynamic systems with many frequencies behaves like a narrow band filter that enhances the excitations that have frequencies characterized by frequencies close to the natural frequencies of vibrations and suppress all the other frequencies. So this is quite interesting and quite complicated and challenging area of structural dynamics and electronics, and that's probably will be all I want to say today about random vibrations. Now, I mentioned that as a rule, and we all know that, we speak in terms of the number of Gs. 500 Gs, 1,000 Gs, 2,000 Gs, how many Gs can this structure withstand, and what should be the excitation, the conditions for an accelerated testing. And the question that I ask myself when we ran these tests on the shock tester, is the maximum acceleration always an adequate reliability criterion? I will not, you can find all the considerations and whatever different reasoning in the paper that was published in CPMT Transactions in 1997. But here I just want on this course to illustrate to you, to show you, when on the physical level, intuitively, when it's clear that there are cases when you have very high accelerations and certainly low stresses, and a situation when you have certainly, you feel intuitively, it can be confirmed, of course, mechanically, you have very low accelerations, but the stress might be very high, and certainly the structure can fail mechanically. Take a look at these two pictures. On the left-hand side, and let's also consider a situation when you drop a structural element which is like a simply supported beam or a plate or a printed circuit board on the left-hand side, and you drop also another structural element, let's say that type that we just addressed with a heavy electronic component, and on the right-hand side, and you drop them both. Take a look. First of all, I want to remind you that in this it's clear that if you have a sinusoidal excitation, the response will also be sinusoidal, although with a different frequency, as long as we don't deal with resonant conditions. And having in mind that, let me show you something. The response will be, I'll write it this way. So it's x, it's a displacement, amplitude, sine, and here this is, as we have agreed, it's a phase, and t is time, and omega is a frequency of vibrations. This is displacement. If you want to evaluate the acceleration, what do? We should differentiate this equation twice with respect to time, and that's what we will obtain. It's elementary differentiation, so you're probably familiar with that. If not, you'll take my word for that. So it's clear that this is the maximum acceleration, because this is the amplitude of the acceleration. As you will see clear from here, the acceleration is proportional to the frequency squared for the given amplitude. Let's go now back to these two pictures. In the first case, if you will see this simply supported beam or a plate, it's clear that after it hits the floor, it will start vibrating with a very, very high frequency. That means that the acceleration here, which is proportional to the frequency squared, will be huge. It's clear also that the stresses in the mid portion of this beam will not be that high. On the other hand, if you take a look at the picture on your right-hand side, with a lamped mass at the end, and you drop it, that it will start vibrating with a relatively low frequency, and the frequency will be the lower, the higher the mass be. Because if you, let me go back again to this view graph. You see the formula for the frequency, even for the same spring constant, if the mass goes up, the frequency goes down. So let's go down back here. So here, the frequency for the cantilever beam with a lump mass at the end, let's say the one that we examined for a heavy electronic component, the frequency will be low, and so will be the induced accelerations. But it goes without saying, and you feel intuitively that the stress at the clamped end might be huge. So, and this illustrates why high accelerations do not necessarily go with high stresses. And it's the stress, not the acceleration, which is responsible for structural reliability. In this connection, I want to emphasize that it's typically the acceleration, not the stress, which is often responsible for functional reliability. In other words, if it's an electrical device, for its electrical performance, optical device, its optical performance. This course, again, is not about reliability, but I want to remind you that usually we distinguish between three types of reliability. It's functional reliability. That's an optical device should be effective optically, electrically, thermal should remove heat, and so on and so forth. Number two, it's mechanical / physical / structural reliability. This device can simply fall apart or exhibit delaminations, cracks, and initiation, propagation, and that thing. And environmental durability, where the system is supposed to be able to withstand high humidity, high and variable temperatures, and so on. So as far as functional reliability is concerned, yes, the maximum accelerations are important. But as far as the structural reliability is concerned, maximum acceleration still might be important. In some cases, they go together with maximum accelerations. I don't discuss it in this course, but if you are interested, read the paper. And there are many examples and situations examined when I show that when the maximum accelerations go together with maximum stresses, and when, as it is in this example, they are different animals. The next problem has to do with dynamic response of electronic systems is, could shock tests adequately mimic drop test conditions? I already mentioned in the introduction to this course that drop tests are often substituted in qualification testing of microelectronic and photonic products by shock tests. Because the shock tests are simpler, you purchase a not very expensive shock tester. You have a freedom to tune the tester any way you want in terms of the level of loading, duration of loading, even the type of loading, whether sinusoidal or constant, suddenly applied, then constant, and then suddenly removed. So you can do many things, provided that you know what you're doing. And in order to understand, but there is certainly an incentive for that. And also you can mimic different drop conditions. And in drop tests, it's not that easy to measure. Of course, what's clear